Okay, very, very, very exciting day. As I mentioned the other day, this next section, section 3.7, is probably one of the most important rules that we're going to learn. It's called the chain rule. It's used in so many places. It is countless. So chain rule pops up when you're using power rule, product rule, quotient rule, any kind of rule. Up until now, I have had to be very careful about what derivatives I asked you to do because you don't know the chain rule yet. That's about to change, and I'm not going to have to be careful anymore. And again, I always tell people how incredibly important this rule is, but I have a very short story that brings my point home. I had a girl years ago who had like a 100% in calculus. Like she was just like never missed a thing. Crazy good at calculus. She came in to her midterm and failed. Like got an F, an actual F on her midterm. And I called her in and was like, hey, what happened on your midterm? And she was like, I don't know. I thought I did everything right. Whatever. So we pulled out our midterm and we started going through it question by question by question. Number 3, you missed number 3. Let me see. You forgot to chain roll. I was like, oh, you silly girl, you forgot to chain roll. Next question you missed. What happened? We're looking at her work. You forgot to chain roll again. Every single question she missed was because she forgot to chain roll. She did everything else right. She did all the calculus right. She forgot to chain roll. It was like for that moment, it just didn't exist for her. She just never chain rolled for her whole test. She failed. Because that's how often it comes up. Okay. So I stress it because it is so, so, so important. The AP loves it. They constantly give us functions that require us to use the chain rule, and they come at the chain rule kind of theoretically because it's a very, very, very important rule. Now, the whole time I'm talking, you may have been distracted by this completely bizarre picture on the screen, and after we discuss what the chain rule is, this may make more sense to you. If you already know what the chain rule is, it may make a slight amount of sense to you already, but what we have here is a very strange woman that has triangular features, and she is pregnant with some sort of what appears to be a turtle, in my opinion. But I think the intention is that it's just a baby. I did not write that caption. When I Googled chain rule, this is one of the images that came up. And underneath it, it said, chain rule, don't forget the baby. And you know what? I chose it for a reason. This is a completely valid image for the chain rule. And I'm about to tell you why. And you're going to be saying, don't forget the baby, or, oh, you forgot the baby. It's going to happen. Ready? My favorite rule. Okay, so first thing that I want you to do is I want you to find the derivatives for me of those 4 functions, f, g, h, and j. Find the derivatives for me. Now, the first thing you're going to have to do if you want to find those derivatives is multiply them out. Notice that they're all quantities, so I don't have a rule for taking the derivative of a quantity raised to a power. So the first thing we're going to have to do is FOIL them all out. So take a moment, FOIL all of those out, and then find their derivatives. Once they're FOILed out, they'll be polynomials, and then you can find their derivatives. Take a moment and do that. Okay, so hopefully you did your algebra right. So let's take a look first at what they look like when they are FOILed out. So once you FOIL them out, they just become quadratic polynomials, right? Okay, when you take their derivatives, for example, f of x just becomes 2x plus 6. Okay, g of x becomes 8x plus 12. H of x in its derivative is 18x plus 18, and j prime of x is 4x to the third plus 6x squared. Now, what I want you to do here is notice a pattern. Okay. Now, it's hard to see the pattern when they are written out like this. So what you need to do in order to see the pattern is pull out a common factor so that you are left with the original quantity you were dealing with. So for example, for f prime of x, if I pull out a 2, move my camera a little bit, I end up with 2 times the quantity x plus 3. And notice that x plus 3 is the original quantity that I had in my problem. I just revealed the next one by accident. Okay, so notice again in this one, if I pull out I started with the quantity of 2x plus 3. Over here I have 8x plus 12. If I pull out a 4, it becomes 4 2x plus 3. Okay, so you factor out the other two and see if you can come up with a pattern that you notice in these different derivatives. How does the derivative and what we know about taking derivatives relate to the original function that you had? Okay. So, in h of x, if you want to factor out to have the original quantity here, now I could just factor in 18 out here, but in order to see the pattern, I want to see what my original quantity here is. So I need to have a 3x plus 3, so I'm not going to factor out an 18, I'm just going to factor out a 6, and I end up with a 3x plus 3. And then last but not least down here, if I want to be left with an x squared plus 3, I can factor out a 4x, and I get left with 4x times x squared plus 3. Okay, so what we know here is that these are absolutely the correct derivatives to these polynomials. What we want to achieve with the chain rule is skipping this step of having to FOIL out. What we want to achieve with the chain rule is going straight from here to the derivative. And I'm hoping that you noticed a pattern here. Okay, so if you notice, we know that if you just have an x squared, that the derivative of that is 2x, right? And here, that pattern actually works. If you take x plus 3 squared, you get 2x plus 3 to the, whoa, to the first power. I can't draw one in there. Okay, to the first power. The rule works. Gets the right derivative. Unfortunately, it doesn't work for any of the other ones. So if I use that same just power rule on 2x plus 3 squared, that would give me 2 times the quantity 2x plus 3. But that's not what I have. I don't have a 2. I have a 4 over here. So the power rule, just using the power rule, isn't going to do it. Same thing down here. If I just apply the power rule to this, 2 times 3x plus 3, doesn't work. I know when I FOILed it out and used the sum and difference rule, I should have a 6 out front, and I don't. If I use the power rule, I only have a 2. Okay. Down here, if I do it, I get 2x squared plus 3 to the first. Okay, well, I have a 2 out front, but I shouldn't. What I should have out front is a 4x. So you may notice there's a piece missing in all of these, except in the first one. There's a missing piece, right? I have a 2, I need a 4. Could I turn 2 into a 4? Yeah, times 2, right? So what I'm missing here is a multiply by 2. What I'm missing here, if I just use the power rule, I end up with a 2 when I know I should have a 6. I'm missing a multiplier of 3. Down here, I should have a 4x out front. I only have a 2. What I'm missing is the multiplier of 2x. And I'm hoping that you're seeing a pattern here. Okay, so for example, you take a look at what you have here, this quantity, and how it compares to your missing factor. What's really special about this one is that the derivative of x plus 3 is 1. So it just so happens that everything turns out okay. But notice that all of these don't have derivatives of 1. Anytime our quantity here doesn't have a derivative of just 1, we end up missing a chunk of our derivative if we just apply the power rule. And that's where the chain rule comes in. Right? I want to be able to give you a problem like this where it's 2x plus 3 to the 27th power and have you be able to do the derivative of it like that instead of being like, I really have to FOIL out something to the 27th power. No, you don't. That's what the chain rule is for. So, what we know is that if you have some power function, but it's a quantity raised to the power, what you cannot do is just assume that you bring the power down and leave this alone and raise it and drop it down by 1. You can't just apply the power rule if your base isn't just an x. The power rule requires that your base just be an x. This is sort of a power rule, but the base is something other than just an x. So what we know is that you can sort of do that, but there's going to be a piece missing. And that piece depends on what this was, what this quantity was. So instead of just having an x, you have some quantity. I like to call it a cloud. You had some cloud. This missing piece out here is always going to depend on what this was. So if we go back to our screen here, notice here the missing piece, I have a 2, I should have had a 4. The missing piece is a times 2. Look here, the derivative of 2x plus 3 is 2. Down here, I have a 2, I should have had a 6. The missing piece is a times 3. Look here, the derivative of 3x plus 3 is 3. Down here, I have a 2, I should have had a 4x. The missing piece is a 2x. The derivative of x squared plus 3 is 2x. So this is my chain rule. They call it the chain rule for a reason. When you take a derivative, it creates like a little chain things, like a little train, kind of. Okay, so I can do this here. I can say, okay, this is definitely going to be 2 times this cloud raised to the first power, but I also have to add on the next link on the chain. I have to also tack on the derivative of what was in this cloud, and in this case it would just be n, right? So the derivative of nx plus 3 would just be n. All right, so let's talk a little bit kind of theoretically about the chain rule, and then we're going to do a couple examples. Listen, if right now you're thinking, what the hell is going on? It is a perfectly normal feeling. Try to relax. Eventually you will understand the chain rule. Eventually you will do it without even thinking. It'll just become kind of a natural thing that you do without even thinking. I promise. I know it doesn't seem that way right now. It's a really strange thing at first, but you will get used to it. You will get the hang of it. I promise. It just takes some practice. Okay. So there's 2 things that I always say about the key to the chain rule. One is knowing when to chain rule, and the other is knowing when to quit chain ruling. Some people get so excited about chain ruling that they just like never stop. They just like chain rule and chain rule and chain rule even way after they should have stopped. Okay, so the first thing, how to know when to chain rule. So you chain rule anytime you have a composite function. In other words, a function inside of another function. You start to see where that baby graphic came from. Okay, I have a function that has another function inside of it. I have a mother function. I have a pregnant function, right? So this function right here, f, is what I call the mother function. And this guy right here is the baby. Right? So notice that g of x, the baby function, is inside of f of x. Anytime you have a situation like this, you've got a chain rule situation. If you have a function inside of a function, you have a chain rule situation. Okay. Here are a couple examples of times we're going to need to chain rule. A couple examples. Okay, number 1. One like we just looked at, x squared minus 4 to the 5th. Okay, this is a composite function. In this case, our mother function is just a quantity to the 5th power, right? I know how to take the derivative of something to the 5th power. It's 5 something to the 4th. Chain rule says, though, yes, but your to the 5th power function is pregnant. It's pregnant with an x squared minus 4. This is our baby, or our cloud. And chain rule says, don't forget about that baby. Here's another one. I've got the sine of something. Okay, I know the derivative of the sine of something. It's the cosine of that thing. Okay, so in this case, our mother function is the sine, And our baby function, yeah, I have to use that weird baby voice when I say it apparently, is our x squared minus 3. Also, you could think of it as your cloud. So this is the sine of cloud. This is cloud to the 5th. I know how to take the derivative of cloud to the 5th. It's 5 cloud to the 4th. I know how to take the derivative of sine of cloud. It's cosine of cloud. I just have to remember to deal with my baby. What's in the cloud? What's that extra piece? What's the function that's inside of the mother function? Okay, here's another one. This doesn't necessarily jump out as one, but you could rewrite this as 2x plus 1 to the 1/2, and boom, you've got a mother function, right? The mother function is the to the 1/2. The baby is the 2x plus 1. Notice the 2x plus 1 is inside of the square roots. The square root is the mother function. What's inside of it is the 2x plus 1. Okay, so if it helps you to think about them as mother functions and baby functions, the baby inside the mother, we have a pregnant function, that's fine. If it creeps you out, go ahead and think about it as composite functions. But I don't know, I found over the years that as weird as it is, it's just, it helps people remember when we, maybe because I say mother function and it catches everybody's attention. I don't know what you guys are thinking about. I'm thinking about composite functions. Okay, so in case you were confused about the chain rule, don't worry. The book is here for you with this fantastic definition of the chain rule. Now I'm going to tell you something. I know the chain rule. I could do the chain rule standing on my head in my sleep if I could stand on my head. This confuses me, and I know the chain rule. Okay, so what they're saying here is they're defining a function y as f of u, which is funny enough. And then they say, oh, by the way, u is defined as another function that I'm calling g of x. In other words, y is f of not just x, but some other function, g of x. They're saying you have a composite function. And if that's the case, they're saying this is the chain rule, this is the rule. Okay. You take the derivative of y with respect to u. In other words, you take the derivative of your mother function and you leave the baby there. And then this is your chain piece. You tack on the derivative of the baby, the cloud. So I'm going to take the derivative as I would normally, leaving the turtle baby intact. And then I'm going to tack on, multiplying, the derivative of the baby. Now, again, this definition doesn't really do it for a whole lot of people. If it works for you, fantastic. If it doesn't, don't worry. We have it in terms of clouds. Now, I will say this. This is the way I'm about to show you is the way I like to think about it. But it also looks scary at first until we put the clouds in. Okay, so instead of thinking it as f of u and then defining u as another function, I just like to put it all together, right? So I'm taking the derivative of a function that has another function inside of it. Notice the rule. I'm going to take the derivative of my f function and leave the g of x alone. I'm not touching it. When I'm done, I'm going to multiply the derivative of g of x. Okay, here's what it looks like with clouds. I have f of cloud. I'm going to do f prime of cloud. Notice the cloud does not get touched, it sticks around. Then I'm going to multiply by the derivative of cloud. That's the chain rule. Derivative of the mother function with the baby left alone, and then derivative of the baby. A couple years ago, somebody asked me how you take a derivative of a baby, and that question still haunts me. We need a new analogy. All right. So again, this is all really abstract. The best thing to do with the chain rule is to watch a couple examples, and then, like I said when I spoke to you earlier, just try them and try them and try them and practice and practice and practice and see if you're getting them right. We're going to do lots and lots of chain rule practice. Okay. So, I don't want to do this one first. We'll go back to that one. All right. So I have y equals the cosine of x squared plus 1. So the first thing I need to do is recognize that I have a composite function here. I have a pregnant function here, right? I've got a function inside of another function. That's the first thing I have to recognize. So hopefully when you look at this, you say, oh my gosh, it's cosine, but it's not just the cosine of x, it's the cosine of stuff, right? that I'm going to call cloud. So in the beginning, when you're learning this, it may help you to rewrite this as y equals the cosine of cloud. Right. If that is the case, then the derivative is going to be the derivative of the cosine, which we know is negative sine. So the derivative of the cosine of cloud is the negative sine of cloud. Then comes the chain rule piece. I have to tack on the derivative of cloud. This is the calculus of it. This is the chain rule. I have said I have a pregnant function. I'm going to take the derivative of the outer function, the mother function, cosine. That gives me negative sine, and notice I don't touch the cloud. Then I multiply by the derivative of cloud. So if I go back and I put my pieces together, this is going to be negative sine of x squared plus 1 times the derivative of x squared plus 1, or 2x. And I'm going to rewrite that as negative 2x sine x squared plus 1. That's our first chain rule derivative. Now, it is worth noting that technically you've been chain ruling all along, because when I gave you the cosine of x, you took the derivative and said negative sine of x. You chain ruled. Your chain rule was just times 1. So everything I've given you so far, it's not that the chain rule wasn't there, it's just if you didn't do it, no harm, no foul, because the derivative was just at times 1. Okay? If the only argument you have, I say the word argument, people ask me what I mean. I'm talking about the thing that you're taking the cosine of, or the thing that you're taking the square root of. I don't know why I call it that, but if all the argument is the thing you're taking the sine of, or the thing you're taking the cosine of, if all that is an x, then your chain rule piece is just going to be a times 1. Okay? That's a pretty rare case, though. All right, let's go to another one. I have the sine of x squared plus x. So again, I have the sine of some cloud. My mother function here is sine. My baby function is x squared plus x. The x squared plus x is inside the sine. So I'm going to rewrite my y function as the sine of cloud. That means that my derivative of y is going to be the derivative of sine. The derivative of sine is cosine. So the derivative of the sine of cloud is cosine of cloud. And then I need to tack on cloud prime. That's the chain rule piece. So again, here we go. I'm just going to plug my pieces in. The cosine of cloud is x squared plus x. And then I tack on the derivative of my cloud, so 2x plus 1. And that's my chain rule. You see that why they call it the chain? So you have the cosine of this, and then whoop, the derivative of that thing. Okay, I want to tell you a really, really common mistake that people make. Notice that the chain rule is that you leave the cloud intact initially and then you tack on the derivative of the cloud. The most common mistake people make with the chain rule, and AP knows this, so they put it out there for you, is they do, instead of writing y prime cosine cloud times cloud prime, they go like this. Instead of leaving this intact, they take the derivative of it inside. Doesn't work, right? This is not, okay. Leave it intact when you're taking the derivative of the mother function, then you take the derivative of your cloud. All right, how about this one? So for this one, I have to rewrite it. So hopefully I look at this and I say, okay, I got a function inside of a function. I've got a square root with something else inside of it. If this was just a square root of x, we would write it as x to the 1/2. So I'm going to write it as 2x squared plus 3x to the 1/2. Right, well, guess what? I've got a mother function here. Mother function is to the 1/2, but I've got this cloud raised to the 1/2. I have a baby here inside of the square root function. So instead of just an x to the 1/2, I've got this cloud to the 1/2. Fine. I know the derivative of cloud to the 1/2. It's 1/2 cloud to the negative 1/2. Chain rule. derivative of cloud. So I'm going to take the derivative of my outer function, my mother function, 1/2 cloud to the negative 1/2, and then chain, whoop, tack on the derivative of your cloud. So in this case, I have 1/2 2x squared plus 3x to the negative 1/2, and then I have to tack on the derivative of my cloud, which would be the derivative of 2x squared plus 3x, or 4x plus 3. Okay. All right, now I want to go back to that secant one, and I'll show you why I skipped that one initially. All right, hopefully you see the cloud here, right? Cloud here is your x squared minus 7x plus 2. Okay, so I have the secant of cloud. I know the derivative of the secant of cloud. Secant cloud times tangent cloud. Chain rule times cloud prime. Okay. A question comes up over and over and over on these types of derivatives, secants and cosecants. They say, do you have to write the cloud both places? Absolutely, yes you do. And then the question comes up, well, do you then have to chain rule twice? Because I wrote the cloud twice, do I have to chain rule twice? No. The derivative of your mother function, secant, is secant tangent. Then you chain rule the derivative of your cloud. That's it, just one time. So this one is going to be secant x squared minus 7x plus 2 tangent x squared minus 7x plus 2, and then times the derivative of our, gotta do like that, 2x minus 7. Again, super common mistake here is to either chain rule twice, or for some reason, people will write like secant x squared minus 7x plus 2, and then they'll write tangent x. The secant originally had a cloud in it, so the cloud needs to show up in both pieces of the derivative, and then it needs to get chain ruled one time. Okay, I know this is a lot. I really do. So please put any questions that you have in the end, and I will check them out, and we will talk tomorrow and do some examples in person before we practice some more. This is the chain rule, right? It's just that you've got to practice and learn how to recognize when to do it and when to quit. And we'll talk more about the when to quit later. Okay, deep breaths. Even if you're confused right now, you won't be soon, I promise. Mark my calculus words. Have a happy day.